Okay, hello everyone. Welcome to OpenHW TV, episode 5, where we'll be talking about the Functional RTL Freeze milestone for our CVE4, which is an open source RISC-V core and part of our Core 5 family. As we've done with previous episodes, we have a whole panel of speakers, and they're all watching together with all of the attendees. We pre-record the content for quality, but I just want to let you know that all the panelists are here. So give a wave to the audience, guys, and let them know that you're live and not a still image. And the content, as I said, is pre-recorded. Please enter your Q&A during the session that our speakers will answer along the way, and we'll also bring everybody back at the end of the session for about 10 minutes of live Q&A once the pre-recorded content is over. So with that, we'll start the live stream of the pre-recorded content right now. Here it comes. Enjoy the episode. Okay, well, hello everyone, and welcome to episode 5 of OpenHW TV. So from an agenda standpoint, I'll give a brief overview of the OpenHW Group. If you're new to OpenHW, go back to episode 1 of OpenHW TV, and there's a more in-depth overview there, but I'll provide a very brief overview in this episode. And then we'll bring in a panel of our verification experts to talk about the path that we've gone through from last June to where we are now, and in particular, the Core 5 verification test bench. So that group I'll introduce in a moment, and then we'll look at more details around the learnings that we've had in the verification work that we've done over the summer. We'll have another panel talking about formal methods that we use to help close verification gaps. And we'll conclude with a panel covering the coverage reports that we're producing and that we'll be sharing publicly to show the quality of the verification work that we've done. And as always, we'll have a Q&A at the end of the session where we'll bring all the panelists back for that Q&A. So throughout the session, please enter your questions along the way. But to get us started, I'll give a quick overview of the OpenHW Group. So the OpenHW Group is a nonprofit organization with a global footprint focused on delivering industry quality open source IP. In particular, we started with the Core 5 family of open source RISC-V cores, which originated life at the University of ETH Zurich under the leadership of Luca Benini, known as the Pulp Platform project. And we are now the maintainers, if you will, of some of those cores, and we'll talk about that in a few moments. But importantly, the focus of the OpenHW Group is to provide that environment for open source collaboration in the hardware domain, and in particular, these open source processor cores, and related IP and software tools to develop an ecosystem around this IP. And our focus is on leveraging the best-in-class commercial development tools and open source tools where they're available, but use the best tool for the job. And we work in a system Verilog UVM environment and producing the kind of quality that you'd expect to see in commercial IP. We have a global footprint with developers from around the world, many different participants from industry, over 57 plus and growing members and partners, large industrial players, in the silicon space, in the system space, big companies, small companies, software tool chain companies, and everything in between. So quite an active and vibrant ecosystem. Academically, we have got very strong participation from some leading academic institutions around the world. And we're also supported by a healthy array of partners and helping us develop these artifacts and bring them to the open source. So as I mentioned, the initial projects within the OpenHW Group are 2 cores based around the Core 5 family of open source RISC-V cores. In particular, the CVE4, which is a 4-stage embedded class core, originally known as RISC-V from the ETH team, and the CVA6, which is both a 32 and 64-bit 6-stage application class core, again from the team at ETH. And now the OpenHW Group ecosystem is the committer if you will, owner of these repositories, and we maintain these open source artifacts for the community. If this is your first episode, we produce these live stream episodes monthly. So this is episode 5, and we're focused on this functional RTL freeze milestone for the CVE4. But you can go back and view OpenHW TV episodes from last June throughout the summer, as we've covered different parts of the ecosystem that are helping us develop these open source artifacts. So with that, we'll bring it back, and I want to bring in a panel of our experts from the verification task group. And we'll have Doug Letcher, who's the CEO from Metrics. We'll have Mike Thompson, who is on staff here at the OpenHW Group as our Director of Engineering for the verification task group. We'll have Simon Davidman from in Paris, and we'll have Steve Richmond, who is an engineering manager with Silicon Labs and is the co-chair of our verification task group. Gentlemen, welcome to the episode.
Nice to be back, Rick.
Absolutely. Good to be here.
All right. Okay. So back in June, we had an episode focused on our verification task group and the test bench that we built. And just as a quick refresher for the viewers, the verification task group is co-chaired by Leo Wang from FutureWay and Steve Richmond from Silicon Labs. And Steve is on the call with us here today. And the focus of the verification task group is really about creating a commercial quality, industry grade verification environment so that people can take the RTL IP for the cores and use them in high volume production SoCs. So maybe if we talk for a bit about the test bench itself and what we have put together. Maybe Mike, I'll start with you as our Director of Engineering for the verification task group. Can you talk a little bit about the environment?
Yeah, sure, Rick. I'd love to. This will be a refresher for anybody who's seen episode 1 of OpenHW TV. But just to catch everybody up, I'll walk everybody through the environment, and we'll go from your left to your right. Off on the left-hand side is where all the stimulus is created. These are usually in the form of test programs. These are either generated by hand, so a human writes a program, C or assembly, or we use the Google instruction set generator. You may know it as RISC-V DV. Either way, these programs run through the tool chain to assemble them into ELF and hex files. The hex file is given off to a Verilog memory, and the ELF is given off to the memory for the reference model. The reference model is the Empirus ISS, and this thing is packaged up as a UVM component in our UVM environment. The key thing here is that the RTL of the core and the reference model are executing exactly the same program at exactly the same time. And at every time we retire an instruction, we compare the state of the CSRs, the GPRs, and the program count. And we call this step and compare. Really a key feature of this environment. A couple of other key features are we have either virtual peripherals that are driven from memory mapped I/O, driving interrupts and debug requests, or we've got UVM agents that will asynchronously drive these interrupt and debug events. Watching over the whole thing is a collection of functional coverage that basically tracks how well we're doing with regard to completeness. This, when we talked about this a few months ago, this was more of a future looking. This is what we're planning to doing. I'm very pleased to say that this is all up and running today, and it runs with all of the major system Verilog simulators.
Right. Okay. So, Steve, maybe for you, the question around within Silicon Labs, you have your own CAD tool, supplier of choice and environment. The importance of commercial grade work here in this open source environment. Can you talk to that a little bit around how you guys have approached working in this environment with us?
Sure, Rick. There's quite a few advantages to being able to really leverage and aligning ourselves with these corporate simulation tools. First, of course, with our advanced verification teams at Silicon Labs, it's quite easy for us to pick up the environment. The individual commands may not be the same, but as soon as you get into the tools, it's quite familiar with both our verification specialists and verifiers. Also, it's definitely lends a lot of credibility, I think, to our project and the work that we're doing. All of the flows that we would typically do for an IP are virtually identical. Some of the commands again are a little bit different, but it also gives us the opportunity to take this open source project, including the verification, and really integrate those into our flows. So we still have the same checklist, the same procedures for finishing up a processor core, the same for any other piece of IP that we would also be able to support as well. And while also giving us the flexibility, of course, in certain environments to be able to use different simulators, which is not an unheard of thing, even in individual corporate environments.
Okay, thanks. Before we get to the workflow, Simon, can you weigh in on the reference model and the way that it's been integrated, with a UVM wrapper, and the importance of that actually in this test bench, and maybe a little bit of commentary on the interaction that your team's had with the ecosystem as we've worked through the summer months here?
Yeah, Rick, yes, of course. So I think that, it's interesting, on the picture you say, there's a block there for the Empirus reference model, but actually there's a lot more to it than just, simple ISS or whatever. And actually, there's been quite a lot of integration work that's had to be done with Mike and his team and the teams and the collaborators in companies in open hardware. And for example, instead of just the reference model box, there's really four things that we've had to work on as a team. The first is the model, and that's really where Empirus has come from, where we've got to make sure we have the functionality correct to be exactly the core that Mike's team's trying to verify there. So the first is the model. The second thing is that there's actually some sort of verification IP in that block that we've built, which is a synchronizer, which keeps the model in synchronization, in sync with the RTL as it's running. And then there's one of the most important bits is actually what's called a tracer, which is technology that monitors what's going in the RTL and provides it out to the test bench. And then there's comparison technology, which there's a block there in the diagram step and compare. So there's actually sort of four blocks that have had to be worked into this environment, working with the teams in different companies to get that to work. And it's been quite an interesting collaborative project to do that, because in our environment, we use one simulator, it's used in regressions with another, and Steve's using another. So there's a lot of the sort of technology that's had to be worked through to get it to work. But it's a very interesting development with this UVM test bench, so it can test not just the initial core, but other cores as well. So it's been an interesting development that we've done. It's available obviously through Mike's GitHub and everything, and we made great progress since the last OpenTV episode. Great.
Okay. Doug, coming over to you from the metrics standpoint and the workflow and task assignment and the execution continuous integration environment that we've got regressions running in the metrics environment. Can you talk to that a little bit of how that's worked and distributed teams being able to contribute to that and working on that?
Yeah, sure, Rick. Happy to. I think the obviously innovative thing about what's happening with open hardware is the distributed collaborative nature of an open source project, right? And that's a well-proven model in the software world that I'm excited to see coming to the hardware world. I think we all are. And typically, when you have that kind of open distributed development model, you have to have a central point of continuous integration, or something that's considered the golden reference of a check-in is good, right? So in the software world for open source projects, traditionally you have GitHub has become popular. Of course, there were alternatives in the past, but GitHub is the thing now, and that's also what we're using here for open hardware. And in that model, you typically have some sort of continuous integration service that runs alongside GitHub and runs your software on a C compiler or whatever kind of software it is. And that's easy in the open source world, because typically the software compilers themselves are open source or freely available and such, right? So, what Metrics is bringing here is that continuous integration capability for hardware with a system Verilog simulator that attaches to your open hardware GitHub, right? And that's meant to be used in a distributed capacity, as Steve spoke to, making use of the Silicon Labs infrastructure for some of his own day-to-day work, but you still need to have that collaborative distributed team central integration point, and that's really what Metrics is providing, I think, to the effort here. And we're very excited to see that in a real-world case of an open source hardware following along the open source software. And of course, that's something that can happen in private projects as well, but open hardware is leading the way in terms of doing it publicly in a way that everyone can follow along. So I think that's great, and I hope we're making a good contribution to it.
Yeah, for sure. Okay, let's jump ahead to really the topic for this episode, right, which is our functional RTL freeze milestone. And what that means, maybe Mike, you can start with, well, what do we mean by that? What is this milestone that we're declaring or just about to declare with our RTL?
Well, if anyone's got any little kids, they'll be familiar with the phrase, "Are we there yet?" And if you've ever worked in ASIC or FPGA development, you're familiar with your boss saying, "Are you done yet? Can I tape out?" And that really is what RTL Freeze for us is all about. At Open Hardware, we're IP providers. We're not necessarily silicon providers. So when is the IP, the RTL, when is it ready for someone to use? So when can, what we're looking to create here is IP that is of the same quality that you'd buy from a commercial IP provider. And there's lots of them out there, and we want to be, they've set the bar very, very high. We want to achieve or exceed that bar. So how do we know that we've done that? Really, it's all about planning and tracking. So we start with verification planning. Some people call this test plans. Some people call them verification plans, DV plans. They go by different names. But really what it is typically captured in a spreadsheet. I know everybody hates spreadsheets, but they're not a bad format for this kind of work. And it's just a laundry list of items that you need to verify. Things that come straight out of the specification, things that come out of the ISA, things that come out of your particular microarchitecture. We're doing a RISC-V core. The RISC-V core has an add immediate instruction. Add immediate instruction has a bunch of features. We need to make sure that we write those down. We articulate to ourselves how we know when a test passes, how we know when a test fails, and how we know when the test is actually completed. And we put all of that into what we call a verification plan. And we have one of those for every high-level feature in the architecture, and this is organized in a hierarchical fashion. If you're familiar with the user guide, the user manual, you'll be familiar with the structure of these spreadsheets. And these spreadsheets are open source information just the same way that our test benches are, just the same way that our RTL is, just the same way that our user manual is. So you can go to GitHub today and see the current state of our verification plans. What we then do is we translate those verification plans into coverage, and this is where Metrics really shines, because once we run a regression, we get to see, hey, we've done this, we've done that, we haven't done something else. So the answer to the question, are you done yet, is have you articulated everything that you need to do in order to know that you're done? Have you captured a way to measure that you're done? And has the measurement completed? And once the measurement's completed for every item in your verification plan, and all the test cases are passing, and there are no known bugs, then essentially you're done. And it's easy to say all that.
Yeah, easier said than done.
Yes,
no
it
question.
is.
Steve, this is maybe a different name, but it's certainly Milestone that would be inside your company developing the products that you develop. How does the functional RTL freeze milestone work that's happening inside OpenHW Group compared to what you'd expect to see in an organization like yours?
Oh, it aligns very, very closely with what we would typically do for a piece of silicon. You know, of course, we've got you know, the physical design guys, even though they're a little bit out of sight, out of mind to some of us guys who do design and verification for a living. They're quite important, and they quite often, especially in advanced geometries, low power, they have their own huge set of complexity. So they've got a multi-month schedule to meet as well. Also, with that complexity and risk that's in a physical design, there's you know, there's a functional aspect and just a general quality aspect to the RTL that we hand off to the physical design teams when we say go. The better it is, the cleaner the timing, the cleaner the code itself is, the better it translates to gates, the better the timing. All of these aspects which are realized within our RTL freeze, not to mention having to do any changes if we find late functional issues, directly affect physical design, directly affects the schedule, directly affects time to market. So it fits quite nicely with what I would do for an internal IP that I would be handing off to the integration and physical design teams.
Simon, Doug, do you guys have any commentary on our RTL freeze milestone to add?
Yeah, I'll jump. So it's interesting. Earlier on, when you were talking about this, I mean, one of the two things that I think the two things that I think are very important. I wrote down, you know, verification plans and coverage targets. Those are from my point of view. You sit at the beginning and you define, as Mike says, what it is, or Steve said, looking at what you're trying to do and what you're going to cover, how you've got to test and how you've got to cover it. You define your verification plan, and then at the end you look to measure that. And what it always does is it raises issues. Well, how, you know, like Steve was working on exceptions, interrupts, and he's going, well, and from a model and synchronizer point of view, we have to go, okay, he wants to test this, so how are we going to make sure the model does what he wants so that he can actually control it and then observe things that he needs to? So that by having a verification plan up front, it means you have to get in place the right sort of infrastructure in the sort of the simulators and the models and stuff like that, so that you can then get out the end with the coverage is done. So yeah, you know, those are the two things I wrote, and Mike, Steve both mentioned those. So yeah, I mean, it's absolutely the way that we see all our customers doing it, which is to get to silicon. You got to decide what you're going to do with a plan, and then work out how you're going to measure it, and then you're done when you've succeeded and got there. You know, with your coverage.
Right. Doug, do you want to add anything to that?
Yeah, just briefly, you know, coverage, of course, is the main goal of, you know, an effort like this. So it's a great milestone for Steve and Mike and team to get to their coverage closure, their point here. And, you know, I think one of the key things there is just tracking that day to day and seeing it kind of go up and to the right. And, you know, I think that's something that hopefully soon we'll be able to share live, as, you know, we're planning to offer a dashboard where, you know, through the sort of GitHub and continuous integration flow that I spoke to earlier, you can watch that process live. So hopefully that will be coming out soon as a feature that we'll provide to the OpenHW audience. Yeah.
Great. Yeah, we'll talk more later during this episode about the coverage gaps and how we've closed them and the progress we're making there. Okay, thanks very much for joining us. Please hang around for at the end of the session. We'll have the audience Q&A, and we'll bring you back on at that point. Thanks, guys. We'll switch it back now and bring Mike back on, Mike Thompson back on, to just talk about what we've learned over the course of the summer and the verification work that we've been doing and how we've modified our test bench strategy as a result. So welcome back, Mike.
Thanks, Rick. So we're going to talk about RTL Freeze and our path to RTL Freeze. And I'll just remind everybody what we mean when we say RTL Freeze. RTL Freeze means that the RTL is all coded and it's all verified, and that you can slap your badge on the table and say, this is done. You can take this to silicon. How do we know that we're done? Well, we have a number of ways of measuring that, and the key thing is that we measure it. We don't just say it, we measure it. So the first thing is to capture and review a detailed set of verification plans. We've been talking about that. We need to map those verification plans into specific coverage, either functional coverage or code coverage or test coverage, something that you can actually measure in an automated way. And we have a checklist. Everybody hates checklists, but we have one too. And all the items in the RTL Freeze checklist have to be completed. So that sounds easy to do. But of course, once you start working towards it, you find out that the path that you need to take is never a straight line. And we certainly had that. As everyone knows, we're using the metrics continuous integration platform for our simulations. The great thing about metrics is out of the box, it measures coverage for you. So you get functional coverage and code coverage right out of the box. You don't have to do anything to get that. So we were doing that, and you can tell that this is real data because we got this crater here on October 8th. That was a bad day for us, but we recovered. But one thing that we were noticing that we weren't getting better at is we weren't getting better at our functional coverage. It was stuck at 50%, and we weren't getting better at our code coverage. It was stuck at about 75%. This was obviously not the right the thing that we were looking for, so we needed to take some action. So we started to analyze that, and we found a bunch of things. The low coverage was telling us some things, and there were really some big rocks. And what were those big rocks? Well, the first was there were bugs in our functional coverage model, particularly in the ISA model. We were just not collecting information the way we should, so we had to address that. We had low coverage in instruction exceptions beyond what the RISC-V compliance test suite was giving us. So we needed to do something to deal with that. And by instruction exceptions, I mean things like illegal instructions, or addressing a CSR that doesn't exist, or writing to a read-only CSR, the kinds of things that would flag the core to recognize an illegal instruction. We also had low coverage on interrupts on debug corner cases. We had good coverage on interrupts on debugs, but the corner cases were almost non-existent, and that was a very worrying thing. And last but not least, we had very low coverage on the instruction and data bus wire protocols, particularly around stalls. So that was another thing for us to focus on. So with all that information, once we dug into the coverage, with all that information, that allowed us to react. And what did we do? Well, the first thing we did is we reviewed and updated the coverage model, and that steered the ship in a good direction for sure. The second thing we did is we talked to the teams doing formal verification, because also in addition to simulation verification, we're also doing formal verification, and we'll be talking about that later. We asked the formal team to prioritize the work on exceptions. Exceptions is the area where formal is particularly well suited. So we asked them to do that earlier rather than later, and that allowed us to get, as a verification team, to get bugs into the hands of the designers quicker than we might otherwise. While that was going on, we realized that we needed to do something a little bit better with interrupts and debug requests. So rather than getting them all from the virtual peripheral and through code segments, we developed a couple of agents. These are, if you've ever done UVM verification before, you know what a UVM agent is. So we created a debug agent and an interrupt agent, and these allowed us to drive random asynchronous debug requests and interrupts and really hammer on those features, and that got the coverage way up. Last but not least, we updated our memory model to add a bunch of random stalls to the grant and the ready signals. We had something in place for this already, but it needed some work, so we attacked that and really got a lot of benefit out of that. So what's our current status? Well, actually pretty good. Our coverage is north of 95%, and we'll be actually in some cases well north of 95%, and we'll be talking about that a little bit later. And so we're going to focus on driving the last yard out of the coverage models, and we also have to knock off the items on the checklist. There's verification planning, code coverage, functional coverage, and regressions. We've got to make sure that everything in that checklist is completed, and that'll get us to the goal line.
Great. Thanks very much. Please hang around so that you're part of the Q&A at the end of the session. Okay, so as Mike alluded to, we have we have a mix of system Verilog simulation as part of our verification strategy, as well as using formal tools to help help close the coverage gaps. So now we'll have a short panel where we'll bring in Ashish Dabari from Axiomized and Sven Beyer from OneSpin to talk about some of the formal work that we've done to close verification in the for the CVE4. Gentlemen, welcome to the episode.
Hey guys.
Hey, Rick, hi.
Great to
Great to
Good.
Glad to be here.
So we have a pretty healthy system Verilog-based simulation test bench. Why really do we need formal as part of this? Maybe I'll start with you, Ashish, and
Yeah,
you can
sure,
give
Rick.
us an overview of
Yeah.
what you've done.
Great question. Yeah, why do we need formal? So we need it because formal is great at establishing proofs of correctness and also establishing that everything works as expected without any corner cases. So corner case bug hunting is excellent with formal, and you can prove things like deadlocks don't exist, like you've actually covered all possible interactions, proof that you have. So those kind of aspects are quite easy to orchestrate in formal, and they can also not be done very easily with simulation. So in a way, that's very complementary. If I actually now give you an update on what we did with CVE4, we started off with architectural proofs, and we established that the CVE4 can work correctly against all instructions in the user ISA. And we could examine this correctness aspect in presence of stalls, interrupts, and extensions. We can prove that extensions do not break the expected ISA behavior. We also carried out deadlock analysis to prove that core doesn't lock up. So we've picked up issues in all aspects of specification, design, glitches in our own test bench, and we validated the results with all of the main formal verification tools that we have in-house, from Cadence Metagraphics and Synopsys. And we rounded off the verification with extensive coverage analysis, which we'll talk about at a later date.
Great, thank you, and thanks very much for your contributions on the project. Sven, what's your take on why formal and how OneSpin has contributed to the CVE4 verification work?
Well, Rick, I mean, one thing formal is really good at is establishing that there's nothing in your core that you don't want it to be there, be it instructions, registers, or of course the weird side effects that could be backdoors for your hackers. So that's why we at OneSpin built a solution around processors and RISC-V in particular. Quite a few nifty automations in there. Let's focus on what we have actually done here in this particular project, right? So we joined the project when verification was already pretty well established for the normal instructions. So the pain point at this point in time was actually the exceptions. So that's why we had an initial focus on exceptions, resulting in a couple of bug reports and code fixes. But of course, we also applied our general ISA-based instruction correctness and found really the classical formal corner case bug that takes lots of ingredients like quite a few stalls, data dependency, and interrupt. The interrupt has to be retracted, and then a debug interrupt. And if all these things come together at exactly the right timing, something wrong happens. And finally, we focused on other aspects of what we call the privileged ISA, or what the RISC-V Foundation calls the privileged ISA. So all these special registers, which typically there's so much special cases in the specification, it's really hard to get right. So also there we reported a couple of issues, and we even had to go back to the RISC-V specification and the sale formal model to raise some tickets there, because some stuff actually was not properly specified there as well. So in a nutshell, that's kind of our contribution to the Core 5 verification.
Great, thanks, and thank you for your work in this project as well. So Mike, your verification guy, dyed-in-the-wool verification guy. So what's your take on why formal?
So we need formal for a couple of reasons. One is just to do with general, industrial grade verification. Every verification technique has its strengths and weaknesses, and It definitely doesn't make verification cheaper to do it with both simulation and formal, but it certainly yields higher quality. There are certain things that formal is exceptionally good at. You know, both Ashish and Sven highlighted specific things that they were focused on that are, you know, that formal really shines at. And, you know, it's difficult to prove in simulation that something can never happen. We can only show in simulation that we've never seen it happen. We've tried to make something happen. We've tried to violate a rule, or we've tried to see that a rule is adhered to, but we've never seen it broken. But we can't prove that it's not broken. Formal can actually prove this. So this is a great advantage. So I'm a big fan of, you know, give unto Caesar that which is Caesar's. So formal is very good at many things in the verification space, and you should give those problems to formal, let formal take care of them. Simulation has its strengths. Let's be honest, I mean, we could verify this whole core with formal. Many of the people that would adopt Core 5 IP probably are not formal experts, don't have in-house formal teams, don't have in-house formal tools, but they certainly will have simulation tools and simulation expertise. So, you know, given the nature of the organization we are and the type of IP we're providing, we have to have a comprehensive simulation environment. So I think owing to the state of verification, owing to the kind of organization that Open Hardware is, it's very important for us to do both simulation and formal, and it's really paid off for us.
All right. Okay, so thanks, gentlemen. One thing to point out to the viewers is we're going to have a deep dive on the formal methods that have been applied to this project on Thursday, the 19th of November. So mark your calendars for that. At 11 a.m. Eastern is the live stream time. We'll have information on that going out on our social media channels in the coming weeks. So thank you for your work, and I look forward to that episode with you. And please hang around for the Q&A at the end of this episode, where we'll bring the viewers in to drive some questions for the panel. Thanks, guys.
Thank you, Rick. Thank you, Mike.
You're welcome.
Okay, so our last scheduled talk for this episode is the RTL Freeze coverage reports that we are publishing publicly. So that anyone can have a look at what we've done and what the coverage looks like. And for that work, we're going to bring Greg Tumbush from EM Micro in, bring Mike Thompson back, who leads the engineering effort for the verification task group, and bring back Steve Richmond from Silicon Labs, who's also the co-chair of the verification task group. Gentlemen, welcome back, and let's talk about our coverage reports.
Thank you, Rick.
Thanks, Rick.
Good to be here.
Good to be back.
Okay, cool. So this is exciting, right? We're getting close to our functional RTL freeze milestone, and part of the way that we know that we're there is by tracking our coverage and using the coverage reports that we're generating to guide what we're doing next. So before we maybe get into some of the philosophy behind that, Steve, if I could throw it over to you, maybe you can share your screen and walk our viewers through what our coverage reports are, how to navigate them, how they were generated. Cadence is a CAD tool partner for OpenHW Group, and I know you guys use Cadence internally as well. Let's just walk the viewers through what we're publishing and how we generated it, and how they can use this information to increase their confidence in the verification work that we've done for the core.
Absolutely, Rick. I'd be glad to. Yeah, as Rick said, based on tools from our partner Cadence, we've been obviously running many tests, many regressions, and here in the last few weeks, we've really been getting to the point of the project where we're trying to make sure that we're done. And to do that we're using what I think you'll find industry standard coverage metrics and coverage tools. And thanks to our partner Cadence, they've really given us the ability to both present something that can be consumed internally, and I believe externally we can also show you exactly the quality of the verification work we've been doing and give you very high confidence that we're delivering what we're talking about. So let me go into the report. This will be available online for folks to look at, in addition to all of our source code as well. So here is an example of a coverage report that we generate from one of our large regressions that we are looking to take our coverage metrics from. Of course, the common metrics that we're using here are the block, expression, FSM coverage for code coverage. The block coverage being, of course, the just making sure that we've touched every line of code. With expression coverage, we're making sure that all of the internal logic, we're catching all those combinations of Boolean and sometimes logic values inside the RTL itself. FSM coverage, of course, making sure that the internal state machines of the core, all the arcs, all the states are properly covered in our tests. And then we do have functional coverage in the terms of assertions, cover properties, and then ISA functional coverage that we'll look at. So for our block coverage, at this point, we're looking pretty good at this point. We do have some coverage that still remains to be hit. So if we can kind of go into any particular area, you'll be able to do this when you access the report online. Everything's really nice and hierarchical. If you're even a little bit familiar with your RTL, or even if you're not, I think you'll find this is something that's pretty easy to go through and kind of see what we're missing here. So by highlighting some particular hierarchy here, we're looking at something in the register block and giving it the metric type. For the code coverage, we decided to really show you what we're missing. At this point, thankfully, we're hitting way more than we're missing. So at this very late stage of the project, so it should be pretty easy for you to go in, see exactly the line number where we still need to be writing tests, improving our randomization, because we're very actively at this very moment making sure that we're adding tests and improving things to hit this kind of coverage. So with lines, it's pretty straightforward. You can see it's either hit or not. If we look at an expression that we're hitting, this is really going into a little bit more detail for individual lines of code, making sure that we hit all the possible combinations of a particular line of code. So if we have an assigned statement here in the load store unit, if we just start highlighting things, you'll eventually get to this table here on the right-hand side, which pretty succinctly tells you a combination of a couple of different signals that the test is not hitting. At this point in time, we are very actively going through these lines that we're missing and determining whether, can we hit these combinations. There will be some that we cannot, based on legal inputs. For those, we will waive, and they'll be removed from future coverage reports. But if they can, we will, of course, write tests that can hit this coverage, and then subsequent reports will be all green. For FSM coverage, if you kind of go into one of our state machines, again, highlighting things, you get a really nice view of how many times we're hitting things, how well we're testing things, so you can get an idea of, we're not just doing one or two directed tests. We're doing lots and lots and lots of random tests that are trying to really exercise these state machines inside the design with all kinds of different other stimulus. Going into the assertion coverage, if I could skip around just a little bit, we've written quite a few assertions internal to the design. And by clicking over to the assertions, you can get, again, an idea of what those assertions are. And if there are any that are missing at this time, we're really close. So we're getting very close to having all of our assertions. And this also covers cover properties. So if there's any low-level signal conditions, especially on external interfaces, interrupts are a very good example that you'll find in this report, where we've self-defined a lot of coverage from our verification plans. You can get proof we've hit all those by clicking down there. Functional coverage, this will be the cover groups using the system verilog cover group construct. This is really where we're self-defining functional higher level coverage of things that we would like to see hit in the processor. Typically for a processor, those would be very much the instruction set architecture. So here at OpenHW, we have defined a coverage model that covers all of the instructions and combination of operands within those instructions that we believe will be absolutely critical to give you the confidence that we've covered everything in the supported sub-extensions of the RISC-V architecture that we say we have. So within this report, you can click down through any of the instructions. They each have a cover group, and you can see exactly that, for example, for this AND I instruction, we've covered all possibilities of the destination register. We've covered all possibilities of the source register for the AND immediate, and then For the immediate 11, since that's sign extended, we want to make sure we hit 0. We want to make sure we hit positive, and also make sure that we hit negative values. So we're very close again with our ISA architecture. We also have functional coverage for interrupts and debug. We think it's very critical for those asynchronous events to be covered with context of what the processor is doing as far as instruction execution at the same time. So those are areas that we're working very hard on, where we've seen quite a bit of good progress in the last few weeks, and we're looking forward to presenting a full coverage model when we go to RTL Freeze. And looking forward to publishing this and to really showing off all the hard work that all the member companies and contributors to Open Hardware have been doing.
Awesome. Thanks, Steve. And I'll throw it over to you, Greg, first. As we said earlier in the episode, the path to done is never a straight line. And I'd like if you could share for your own business practices internally, how do you guys define done, and how do you use these kinds of coverage reports internally to inform when it's okay to tape out?
Yeah, for sure. So what the coverage really brings, so we're mainly using functional coverage, where we're tracking to see that the randomization that we're inserting is actually stimulating what we think it's stimulating. So if we kind of think back to the way we used to do verification with directed tests, you would get together with with all the verification people at the end of a project. That these people may span time zones, different countries. The work may have been done years ago, and then you're going to ask somebody, did you cover this? And chances are the answer is probably going to be yes. Right? So now with coverage, you actually take the human element out of it, that you can track, you have hit this. And also coverage can change throughout the project. Let's say you have coverage that's hit, and then some new feature is added to the design or to the test bench, and now your coverage isn't being hit anymore. So it takes it away from being a single point in time in which something is covered to the span of the entire project. And again, it's really required for randomization. And I think we have already found situations with the Open Hardware Test Bench where the randomization that was in place was not giving us exactly what we thought we were getting. And so that indicated a test bench issue, and that was tweaked, and now we get the coverage that we want.
Yeah, that brings up an interesting topic, and all three of you maybe comment on this. Might bring you into the discussion too. So that some of the tweaks that we made to the test bench, specifically as a result of seeing the lack of coverage or coverage gaps and around some of the randomization. Can you explain where those were and how we found them, where they were, and what we did about it? Want to start there, Mike?
Sure. I'll give two specific examples. The first example is one that we've touched on briefly already, and that's the instruction decoder. We were looking at and this is code coverage, so this is coverage of the actual RTL code. And when we looked at that coverage, we saw that we really, were not, randomizing our instructions as much as we should. Weren't hitting some combinations of instructions that were very important to hit. And that caused us to do two things. The first thing is we started working with our partners doing formal verification and asked them to prioritize the decoder verification that they were doing just to get the bugs into the hands of the designers earlier, giving some runway to the simulation team to increase their coverage. The second thing we did is we turned to the Google generator and just turned up the heat and started cranking up more and more and more random instructions. So we just added more randomization to the environment, and those two things took care of the decoder pretty handily. And our code coverage now in simulation for the decoder is north of 98%. The other thing that we did is around coverage on the instruction and data bus for the memory interfaces. We really weren't doing enough to randomize stalls on those interfaces. That showed up in the coverage right away. And this was work that Steve Richmond himself actually did. He rewrote the stall model for the memory, and integrating that component into our environment really brought the coverage up, right up to where we wanted it to be. So what those highlight is what you use coverage for. You use coverage to direct your actions so that you're actually targeting the things that you're not verifying and not just re-verifying something that's already well tested.
Right. Steve, you want to comment any further on the stall models and the work that was done there, that you did there?
Sure. Yeah, it was really quite obvious, and that's really why we do all of those metrics. I'd highlight the functional ISA coverage has been quite good for a while. We were especially if we cranked up the RISC-V generator, as Rick said, or as Mike said, we were able to really see those numbers go up. We were able to see the instruction decodes go up, but that's why it's also important not just to have the intent there, but also to really take a look at what the design's doing, kind of see what you don't know. We can know what we're stimulating the design with, but sometimes cross conditions of other things that are occurring in the design really need to be looked at as well. And it doesn't take too long when you start climbing through some, especially some missing block coverage where you're just missing entire lines. And if you see that ready signal from the bus coming, it's a good indication that there's some combinations you're not hitting. So it was a good feedback and another good reminder and a good lesson for all verification engineers to kind of look at both things, look at the intent and look what's really happening.
Greg, maybe last question over to you. Were there some particular block coverage gaps or issues that this highlighted for your team that you really wanted to see extra focus brought to, either that you guys did, brought to the table, or the other members picked up?
Yeah, but in two areas. It would be the interrupt coverage was very important to us because we knew that was an area that hadn't really been stimulated much with the Zurich team. So we wanted to see good coverage on the interrupts, and then also on the instructions, we wanted to see good coverage with all the operands. Not just using the same A0, A1 operands for the instructions. Two things also I'd like to point out is that remembering or going back to the coverage report, those bin numbers are the number of hits. So those are in the tens of, and I'm trying to remember, tens of millions of hits. So that gives you an idea of how many vectors were run through this device. Even some very specific coverage bins like zero, like was an operand 0, were hit, I think close to 1,000 times. And also, again, I think that's where the functional coverage for me is really the huge value, is that you can write one line of RTL and write something that covers that, and you have 100% code coverage. It doesn't mean you've actually tested anything. Right? So code coverage is worthwhile. It definitely needs to be 100%, but it definitely doesn't give you the full picture.
Right. Required, but not sufficient.
Correct.
All right. Well, thanks, guys. Hang around because we're going to throw it open to questions now from the viewers, and we'll be live on a Q&A. So just before we do that, to the viewers, I want you to make sure you go to our GitHub repo in the README section of the verification test bench. We'll have links to where you can see these reports. We'll be updating these reports weekly. The data is static, but we'll be taking snapshots of the data with our coverage tools and updating these reports weekly to show you how the verification work is being completed. So thanks again, guys, and we'll be back in a moment with the Q&A.
Awesome. Thanks a lot, Rick.
Thanks, Rick. Enjoyed it.
So we have about 10 minutes left before the top of the hour for some Q&A. And one of the topics that came out, or one of the questions that came out that I'd like the panel to sort of comment on, was related to this test bench that we've built and the infrastructure that we have now. Are we going to use that across other Core 5 cores? Will all of our cores be verified, using this flow, or can you even do that? I know you've all probably have opinions on it. So, Mike, if you want to start, everybody should sort of chime in as you see fit on that topic.
Hey, sorry, Rick. I must admit I was I was distracted looking at the question bar. So if you could repeat your question, I apologize.
It was a question. Sorry, yeah, it's the question around reusing the test bench across multiple cores, different cores, and what the strategy is behind that, and how that might work.
Yeah, that's definitely a strategy. One thing that people sometimes get confused on when they come to OpenHW's GitHub repositories is they'll go to the repository for the core. So in this case, we're talking about the CVE32E40P. They'll go to that repository and they don't see a UVM verification environment there. And they don't see any test plans there, and they don't see a lot of the verification stuff that they'd expect to see. That's because we maintain our verification code in a separate repository, cleverly called Core5Verif. And the reason we do that is Core5Verif is intended to be the verification platform for all of the Core 5 cores. So the CVE32E4 cores, the up-and-coming CVA6 cores, any future cores that we would do would all be verified using that environment. And really how we do it is the UVM environment that sits on top of this is more or less constant. Where things will change is functional coverage, assertions, and what we call the core test bench. The core test bench is a low-level Verilog module that where the core actually sits, the RTL model for the core, and of course that's core specific, and the memory model that we've talked about previously, and that's core specific as well. So that's where all the core specific stuff happens down, at the lowest level of the environment, and all the reusable bits are up in the UVM environment. So, and we do plan to be able to reuse those as we go from core to core to core.
Mike, which also means that when a person wants to use our test bench as a starting point for their own cores, it's going to have a common look and feel that they're used to. We're going to have UVM agents to drive the interrupts and the debug. So the fact that we're going to be able to use this core in multiple projects also means that other users can use this for their own projects easily.
Yeah, something to add maybe to it is part of the strategy all along with developing this test bench is we believe we're building, certainly from an open source stimulus standpoint, we believe that we're building the most comprehensive and robust RISC-V verification platform that's available in the ecosystem. And even if you don't use the Core 5 cores, I mean, obviously we think you should, but even if you don't use the Core 5 cores, you should feel free to participate and engage in this test bench development and use it for your own cores. I mean, it is a RISC-V based system Verilog UVM environment for verifying RISC-V cores, leveraging traditional commercial tool flows that the big guys use, that anybody who's producing volume silicon really does use today. Any other comments on the reusability of the test bench and the strategy that we're following from anybody else?
Just a little plug. So Greg and I and Steve and a few others will be co-authoring a paper that's being presented at DVCon 2021, and we will talk exactly about how to use Core5Verif to, how to use it to verify your core, not just our core.
Yeah, perfect.
Just to follow on your comments, Rick, we're available, we're aware of two users right now that are already have already picked up the Core 5 verification environment, but have modified it for their own cores. So it's certainly something that can be done there. It does, as far as we can tell, it is absolutely the best verification environment out there in the RISC-V community.
That's the beauty of open source collaboration. And, I mean, it's great that you say nice things about Core5Verif, Larry, but really, we're all standing on each other's shoulders here, right? We're not standing on the shoulders of giants, we're standing on each other's shoulders. I mean, we're using the best in class reference model from Empirus. We're using the Google generator. We're using test cases donated by member companies all over the place. It gets done when we all work together.
Absolutely.
Okay. Let's stop with the love affair going on there. We'll move to the next question here. So, one of the questions was, coding style and formal, and how do we get formal assertions in here, and how do we just deal with the fact that there's basically stuff coming from anywhere, potentially a pull request being put up against the repo, whether it's the RTL or whether it's the verification repos. How do we deal with that from a consistency and awareness and quality level before we decide to merge and integrate a pull request?
If you don't mind, Rick, I know I've already answered one question, but I'd like to jump in on that one.
Okay. Feel free.
This is the open source community has solved this problem, and we're just merely following along. So it's not like anyone can just dump in code and willy-nilly and have it have it integrated into the environment. We use GitHub. GitLab has an equivalent thing, but with GitHub, when a contributor wants to contribute code, they issue what's called a pull request. That's basically saying, hey, I've got an update. I've got some new code for you, or I fixed some code or something like that. I want you to look at it and see if you can integrate it into your environment. So it gets reviewed by myself or other members of the team, and that constant feedback to contributors is what makes sure that the code that gets integrated in, meets the level of quality that we need, and fits in the Core 5 Vera flow, because we have, as you would expect, a particular way of doing things. It's not right, it's not wrong, it's just a particular way of doing things. Sure. And I was worried when we first started this that would really turn people off, but it doesn't, because everyone quite quickly, when they get the feedback about, this is how we handle integrating UVM agents into our environment. Once they get that feedback, they're happy to oblige, and good things happen.
Maybe Greg and Steve, from commercial users of these open source artifacts, how are you guys satisfying yourself that the quality of what's coming through is okay, is good?
Yeah, from our perspective, you could have a huge list of pluses and minuses for open source development, and really from our perspective, I think we've initially kind of used to being the experts, kind of used to being the frontline engineers who are always able to push things into the repository and kind of what we say goes. However, from being in this flow a few months, and if you write code, you write bugs, and it doesn't matter who you are. I mean, the experts, it's one of my commits, or it's a commit from halfway around the world. I really would encourage you to go to GitHub and look at. We've had lots of back and forth on nearly all of our pull requests. We take that oversight very seriously, and just that kind of mini code review that this flow enforces really gets us to higher quality code faster in the long run, even if it does take a little bit longer to push an individual commit in. Although we're available at pretty crazy hours, so there's usually one of us available to look at things. I'm not looking at Mike at all. But in fact, that's something I'm kind of thinking about pulling, internally a little bit. So a questioner brought up the issue of code reviews, and those are certainly done in the classic sense. And internally, we would do those, kind of near the end. It's something it's too easy to push off. This flow forces you to do that, and I think I can't tell you how many little bugs, little issues, overall improvement of quality that we've had by being disciplined and sticking with this flow. And GitHub really enables it quite well. It's pretty easy once you learn it.
Cool. Greg, you got anything to add to that?
Yeah, so a user of this IP needs to treat it just like any other piece of IP that they're looking to buy. They need to look at the verification plans. They need to look at the coverage reports. The difference here is that it's open, right? Everything is available for you to see. We have no incentive to hide potential problems. In fact, we want to see potential problems so we can make improvements. That's really the difference here. So again, you just need to do your due diligence, just like you're buying any piece of IP.
Cool. Well, I know that not everybody got a question, but we're past the top of the hour, and I want to be respectful of everybody's time, certainly the panelists and our attendees as well. Thanks for joining us today. This entire session, including the Q&A, will be available for on-demand playback. And watch out for episode 6 on November 19th, where we'll be doing a deeper dive into the formal work, and Mike's already started working. There we go. Thanks, everybody.